We used the National Instruments software LabVIEW installed on the PXIs to control the VLC transmission. LabVIEW is a visual programming language where the user creates module blocks known as VIs with inputs and outputs, with variables passed into these using wires, making it easy to track the flow of variables through the software. In addition, every variable in a VI has a visual display on the front panel that shows the variable's value while the code is running. This means that every VI we wrote came with a graphical user interface which allowed us to see the data at every step of transmission process. The graphical nature of LabVIEW, as well as many drivers that came with LabVIEW, made it a natural choice for us to use. Here we see the transmitter VI used in our system. We can control the data to transmit as well as its parameters. See the live feed from a webcam. Observe the transmitted constellation and the transmitted waveform. The user has the option of selecting the type of data to send. They can choose from random bits, a string, or a picture transmission. If the user selects random, they must first choose a random seed to accompany it. The seed is used to generate the pseudo-random sequence, and the same seed will be used in the receiver to regenerate the sequence after transmission and compute the bit error rate. If the user selects a string, they must input the string to be used below it. The receiver has the option of allowing the user to input the same string, once again, in order to calculate the bit error rate. The most interesting transmission type, however, is picture. We've interfaced a standard webcam with the transmitter VI, as you can see on this display. If the transmitter is set to picture, then when the user hits transmit, the image is frozen in sent image. Since we're using a webcam and not a given image, such as a JPEG, we do not calculate a bit error rate for picture transmission. However, since the image freezes, the user can visually compare the received image to the original. Furthermore, the user has several degrees of freedom over the transmission itself. They can specify the packet length, which is the number of bits to transmit, and the modulation type, where they can select between quadrature or binary phase shift keying, or on-off keying. They can further set the symbol rate, carrier frequency, and oversample factor. We run the code to turn the LEDs on, and when we transmit, we see the transmitted constellation as well as the transmitted waveform in the front panel. The receiver is structured similar to the transmitter. There are certain user controls, and when transmitting, we can see the eye diagram, the unequalized and equalized constellations, and both the received data and received signal. Since we have not implemented any sort of protocol, we must match the receiver parameters to the transmitter parameters, including the data type. As we mentioned, under string or random bit transmission, the user can input the string or random seed for bit error rate calculation. The last of the user controls is equalization, where the user can choose to apply an equalizer, a frequency offset corrector, or both. When it is run, it constantly reads the input from the photodiode, checking for a triggering sequence that denotes the start of transmission. As soon as it's detected, signal processing begins. The eye diagram is used with BPSK to see the clarity of the received signal. The two constellations shown are before and after a linear least squares equalizer is applied to the received signal. The waveform shown is the raw waveform received before data processing, and the data received block contains the received decoded picture or string.